So now let's look at our output resistance of our shunt series connection. So what we're going to do here is we're going to use the same type of method we did when we were looking at our voltage amplifier, and that is to use our test source method. So our test source method involves placing a test source at our output, and then we also have to deactivate any independent sources in the circuit. So deactivate our independent sources. So the first thing we're going to do is we can come over here to our output and we can say let's get rid of this short circuit that we had. And so let's add in a test source. So our test source, if we're doing it analytically on paper, we can make this a test current source or test voltage source. Doesn't really matter because either way we're going to have a current of Ix and a voltage of Vx. Okay, and then ultimately of course what we're doing is we're going to be finding this output resistance looking in here. So we're trying to find our output resistance R sub OF, and this is just going to be equal to our test voltage divided by our test current, the same as we saw with our voltage amplifier. So now on our input side, we notice we have this dependent current source for our independent current source for our input current. So we need to get rid of this. So we're deactivating it. And so remember, to deactivate a current source, we replace it with an open circuit because we can have zero current in an open circuit. Okay, so now we're ready to analyze this to find our output resistance. So first we can look at our left side. So we notice without this current source, we no longer have an IN, so we don't really have any current flowing in these areas here. So we're still kind of neglecting that RS value. And so what we see is the only path for our current is we just sort of have this one loop where we have our I epsilon and our I feedback defined. And so we can see that we actually have I epsilon is equal to negative of our feedback current. And what we see now is that instead of having an output current over here on the right, that this is actually equal to beta I times Ix. Because our Ix current, so let me change colors, our Ix current is of course flowing here, here, and then back up here to where we've defined it. So this is our Ix. So we can say this is equal to negative beta I times Ix. Okay, so now let's switch our attention to our right side. And what we want to do is we want to find our Vx. So we want to find Vx. Well, from Ohm's law, we know that our Vx is just going to be whatever our current is in this resistor times the resistance R naught. So we're looking for this current in this resistor, and we can find that by doing a KCL at this node here. So we can say Vx is equal to Ix, which is coming into that node, minus our A sub I times our error current, because that's the current coming out of the node to the left, times that resistance R naught. So now what we can do is we can substitute in for our definition of error current we found up here. So doing that substitution, we get that this is Ix minus AI, and then our error current is equal to negative beta I times Ix, all of that multiplied by R naught. So we can clean that up a little bit, factor out our Ix, so we get Ix times 1 plus beta I times A sub I times R naught. And so of course from here we can easily rearrange that to get our Vx over Ix, which remember is what we were initially looking for. So we can say our output current of this, our output resistance of this amplifier, ROF, is equal to Vx over Ix, which we just rearranged the above equation. We see that that is the quantity of 1 plus beta I times A sub I times our output resistance of the amplifier, R naught. So what we can see here is we're actually increasing our output resistance compared to without our feedback. So increased output resistance. And so this is, again, as you might expect, desirable for our current amp. And so we can think about that if we look again at a simple current divider circuit. So we have some current that is coming out of our amplifier. So maybe this is our I amp, so this has been amplified. It's coming out, so we can think of this as sort of the current coming out of our dependent source. We're then going to have this output resistance associated with the amplifier, and then some load resistance RL, and this is going to be our load current. So I sub L. And so of course we want that I sub L to be as close to our I amp as possible. And so what we can see is that if our RL, or sorry, our R out, so this should be our R out F, if our R out F is large, then more of the current is going to want to go through this direction. So we could look at our current division equation the same as we did previously, but we can also just think about this qualitatively in terms of our current wanting to take the path of least resistance. So the larger this ROF value, the less the current is going to want to go through that branch. So now we're ready to put all of these pieces together in order to make the equivalent circuit for our current amplifier, our shunt series. So our equivalent circuit, using our transfer function, our input resistance and our output resistance, we have something that looks like this. So we have our input current, our source resistance, and then we have our input, our equivalent input resistance to our amplifier with feedback. So we have our amplifier is amplifying this by some closed loop gain. We're going to have our equivalent output resistance, which we just found previously in this video. And then we have some load connected to our amplifier. So let me come back through and label everything now. So this would be our input current. This would be our source resistance, RS. And let's go ahead and label this as our input resistance of the amplifier configuration, RIF. And so if we're not neglecting our source resistance, RS, then this current, of course, is going to be different from our input current. So we can call this I sub I primed, so our input current primed. So then over here on the right side, we have our closed loop gain for the amplifier, A sub IF, multiplied by that I sub I prime. We also have our output resistance of our amplifier configuration, and then finally our load resistor RL, and we would have our output current defined like this. So of course everything in this green area here represents that amplifier configuration with feedback. So now that we've looked at these two basic configurations, we're going to do an example, but we've looked at how we deal with having series connection on the input, shunt connection on the output, as well as shunt connection on the input, series connection on the output. So our other two ideal topologies are just going to be variations of those combinations. So we're not going to derive that as much, but we are still going to present the results.